All right, so we're running short on time, and I'm going to cover lenses in this video. I think you're going to find that a lot of the information kind of complements what we found about mirrors in class. And we are even going to use the same equation. So I think it won't be, excuse me, I don't think it'll be too hard. Okay, so lenses come in a variety of shapes, and here are just some pictures of lenses. And I know that you will eventually do a lab working with them. Just like mirrors, lenses can either be converging, which will tend to bring light rays together once they pass through the lens to focus an image. And they also have diverging lenses, which will actually disperse the light rays. And if you might be thinking, will form virtual images. One of the ways that you can actually tell a lens, whether it's converging or diverging, is converging lenses tend to be thicker in the middle, and the diverging lenses tend to have a thinner middle compared to the edges. So what happens, the way that lenses work, and we really kind of gloss over this and get right to the very simple lens equation, is that you have refraction happening at two different interfaces, the front side of the lens and the back side of the lens. And that refraction actually is helping the light rays to become focused at a location to form an image. But the first thing that we're going to do is we're going to think about how do we define the focal length of these lenses. And we're going to find that it's really basically the same as we had with mirrors. So in this picture on the left-hand side is a converging lens. We see it right here. Here's my converging lens. And just as I did with mirrors, in order to find the focal point and the focal length, I imagine light rays are coming in from very far away, so all the light rays are parallel. And as they go through the lens, they will be converged, they will bend inward, and they all intersect at a common point, and this is called the focal point. The distance from the focal point to the lens is called the focal length. For a converging lens, the focal length is a positive value. This is similar to, if you remember, converging mirrors, which were concave mirrors, also had a positive focal length. In the second picture, we have what we call a diverging lens. You can see it's thinner in the middle. What happens is when the parallel light rays go through the lens, they tend to be dispersed, or diverge from each other, which is why we call it a diverging lens. In order to find the focal point for these light rays, we trace them back to see where they appear to have originated at, and that common point is called the focal point. The distance from that focal point to the lens is the focal length. And in this case, just as it was with mirrors, for the diverging lens, the focal length is going to be negative. Here is another picture, another slide where we're just sort of focusing in on the converging lenses. And in this picture, one of the things is to notice that we consider the focal points to be on either side of the lens. We can think of, for instance, light rays that originate at the focal point on the left-hand side of the lens will actually pass through the lens and then be focused in to be parallel to each other as they go through the lens. And we can say the reverse is true. If we have the light rays coming into the lens, that they're parallel with each other, they will converge on the focal point at the other end of the lens. The lenses that we're going to work with in terms of the values have a single focal length, even though they are showing two different focal points. You can see that they're equidistant, so they have the same focal length. So we don't have to think about that there's two in terms of worrying about the mathematics. We're doing the same thing here with the diverging lens. So for the first picture, this might be kind of tricky, but because the focal point for the left-hand side of the lens is actually located on the opposite side, we draw the light rays as if they were going to pass through this point, F1, right here. And then, but once they get to the lens, we allow them to be refracted or bent, and then they end up going parallel. And that's it's analogous to the picture we saw with the converging lens, but different because the lens is acting on the light rays differently. And the bottom picture we see is more what we introduced when we introduced the focal length and the focal point of the lens. Again, just to remember, diverging lenses have negative focal lengths. Here's a picture of a ray diagram for an image formed by a converging lens. Again, I would want to reference you to the video where I did the ray diagrams, just to talk about what are the rays that we use and how we draw them. And I also mentioned that you don't have to do this, but it's just nice to kind of know how it works. Notice our object is to the left of the lens, and because then we assume that the light is coming from this side, it goes into the lens and then comes out on the right-hand side. We look at the object and we do our three principal rays, and where they intersect over here is where the tip of the image is, because all the rays came from the tip of the object. We see that that image is inverted, but we also would call that a real image because of the fact that it appears on the side of the outgoing light, the light going out from the lens, which is where we expect it to be. And so this has, for a converging lens, the image is a real image and it has a positive image length. Here we see a picture of how we would do the ray diagram for the diverging lens. These ray diagrams are a little trickier because we have to end up tracing back the rays to see where it appears that they originated. Here we see that the virtual image actually appears on the same side as the incoming light. Right here it is. And in that case, it is absolutely a virtual image. I always think of it, virtual images appear to be where you don't expect them. For instance, a real image for a mirror would appear in front of the mirror. A virtual image for a mirror appears behind the mirror. And now for lenses, it's switched just because of the nature of the device. Lens, we assume the light will pass through it. And so we expect the image to be on the side of the outgoing light for the lens, which in this picture would be to the right of the lens. But when we see the image to the left of the lens, which is in the side of the ingoing light, we definitely know that this is a virtual image. You can see that this virtual image is upright, but also note that because of where it's located, its image distance would have to be negative. Now here is another picture that shows just different scenarios for how you would see images being produced. The first two pictures are for converging lenses, and we actually see that a converging lens, just as a converging mirror, can form both real and virtual images. In both cases, what happens is if the object is placed closer to the lens or mirror for a converging lens or mirror, then you form a virtual image. as long as the object is further away from the lens or mirror than the focal point, you will get a real image. For a diverging lens, you always have a virtual image. So it turns out that we get to use the same equation, the lens equation, that we saw with the mirrors. So we might want to just review what are our sign conventions. The focal length is positive for converging lenses. The focal length is negative for a diverging lens. The object distance, that's the distance the object is from the lens, is greater than 0 if it's on the side of the incoming light. That is, if you're when your light comes into one side of the lens and then comes out on the other side. I think you had an example in your lab where you actually had a virtual object where the object distance is negative if it's on the side of outgoing light. It's very unusual, and we would only have that happen if we were using more than one lens at a time. When you have more than one lens at a time, you first do the object forms an image through the first lens, and then that image becomes your object for the second lens. But I don't think you won't have to do that on any sort of assessment. Finally, our image distance is greater than 0 if the image is on the outgoing side of the light for light. And this is a real image. And the image distance is less than 0 if the image is on the side of the ingoing light. And that's when you have a virtual image. I actually find it a lot easier in terms of thinking about where the real images would be and the virtual images would be is for a lens, I expect you have object, then your lens, then your image. That's my expectation. And when that happens, I have a real image. If I have an object, and then an image, and then the lens, that is not what is expected because you expect the light to pass through the lens to form the image. So when I have the image in front of the lens on the same side as the object, then I have a virtual image. The magnification rules are exactly the same as they were for a mirror. So we look at whether M is greater than 0 or M is less than 0, tells you if the image is upright or inverted. That just means right side up or upside down. And we look at the absolute value of the magnification to see if the image is enlarged or if it's reduced. So if that absolute value is bigger than 1, then our image is bigger than the object. If it's less than 1, our image is smaller than our object. And so let's look at some examples. This is sort of a tricky question. You might not expect it. So it says we're putting an object, so here's our object, in front of a lens, and we're going to form a image. Here's my image. And they're basically saying, what if I use black paint to cover the bottom half of the lens? So like, what if I block this out? And they're asking you, like, basically, do you think that the entire, will the image be like cut in half, or what is it going to happen? But if you look at the ray diagram, you see that actually blocking off half of this lens really doesn't affect those rays. And the fact is we only drew two rays that might come from the tip of that object, where we could draw countless rays that would come from the tip of that object and the rest of it. And blocking off half the lens is not going to affect the production of the image. The entire one image will be visible. Okay, and so here's a problem where we have to work with our object distance and our image distance and our focal length. Okay, let's look at this problem. We're going to use this lens equation. And we actually are given some information here. We have the focal length. It's a diverging lens, and that's why the focal length is negative. Here we're given the height of the object. We're going to use that later because this question is actually asking us to find the height of the image, and we'll see how magnification can be used to do that. And here we're given the object distance. So let's put that information into the equation. I have 1 over 24 plus, 1 over image distance equals 1 over minus 12. So let's do our algebra. So you can see that we have gotten a negative image distance, which is not surprising because we had a diverging lens, so we knew that we were going to have a virtual image. Now let's look at how we can use magnification to actually answer what they want us to find. The magnification, in its simplest use, is simply the height of the image over the height of the object. But we've also learned to express it in terms of the distance, the image distance over the object distance. So we're going to use these two things together. And so it actually turns out that the magnification of this lens ended up to be a third. So because that's the ratio of the image distance to the object distance is actually the magnification here. It was a positive 1/3 because the virtual image was going to be upright. That's not really wasn't asked. But we take 1/3 times the original height to get the image height, which is 3 centimeters. This question I find maybe is sort of dated because I don't know if you've used a slide projector. The idea here is that, we sort of have this slide, and then this becomes your object. We're going to have a lens. And the idea is that we want to shine this onto a screen. We have some sort of light back here. Doesn't really look like that, but that gives you a sense. We're told the focal length of the lens is 104 millimeters. And the distance from the slide to the lens was 109 millimeters. That's the object distance. And we're actually trying to figure out this distance because we want the image to be focused on the screen. So it has to be placed at the proper distance. in this case, although we weren't told, this focal length has to be positive. Our lens has to be a converging lens, or we're not going to be able to put a image on a screen. We can only get a real image on a screen. A virtual image would not appear on a screen. So this one I couldn't do my fancy adding fractions, just sort of reverted to doing a calculation. If I do that, I find the image distance of this is 2,267 millimeters, which might be more useful to write as 2.267 meters, even though I probably have to stick with millimeters to do my calculations. It basically says if this is the original size of the slide, so this is really akin to the object height, although we have 2 dimensions. We want to know how big the image is going to be, so we're really looking again for magnification. Since in this case we have a real image, we actually get a negative magnification. All that means is when the image comes up on the screen, it inverts the object, so we have to put in our slide projector, we put our slides in upside down so that they appear right side up on the screen. So I'm really only concerned about the 20.8. This is how much bigger it's going to be. So if I take 20.8 times my width, which is 21 millimeters, and my height, which is 33 millimeters, I'm going to multiply both of those by 20.8. The image on the screen ends up to be 436 millimeters by 686 millimeters. And that's how I do that. So I know we rush through lenses and mirrors, but I think you'll agree that the math isn't terribly difficult. It's a little bit easier than what we've done before. And hopefully this is a good enough coverage for you.